Hello everybody. Today's lecture is about the control signal and the integral wind-up and anti-wind-up. Now we have a transfer function, a signal transfer function, which is given as follows: 40 divided by s squared plus 15s plus 20. Now we have basically four tasks here. One of them is to design a controller, API controller, with a closed loop settling time that's given. And interestingly, we have also a rise time specification given. So most of the time we are used to overshoot and settling time, but here we have some mix up and we have the rise time and settling time. So we'll look at that. And our second task is to plot the control signal. Up to this point, we didn't consider the control signal. We were just looking at the output, especially at the step response of a system in open loop and closed loop. And we've compared how we did change the behavior of the closed loop step response. Basically, the control system. Now we will look at the control signal. We will see what the meaning of the control signal is and what the important aspects about the control signal design is actually. And then we will have some limitation on the control signal, a very simple saturation element which has some negative and positive values. So it will limit the control signal, which is very useful and which is basically very practical. In most real-world applications, you don't have a linear system that is linear in all possible values or for all conditions. Sometimes you have some upper and lower limits where you can work, where you can have restrictions, and it's very important if you have API controller and a restriction. We will see what the effect will be, and we will see how to overcome that effect and how to solve this problem if there's a problem. And then we will compare the wind-up and the anti-wind-up response, and we will see what the end result will be. Now, basically, we can start with the system here, and with our specifications, we can go ahead and define our system, our specifications, and try to implement our controller. Now, as I've mentioned before, we have settling time and rise time. So let's start with the specifications here. So I'm going to define the system using the transfer function object. It was 1, and we had 1, 15, and 20. So I'm also going to define the symbolic toolbox version. So it's basically a fraction that represents the system here, which is s squared plus 15 times s plus 20. And then, since I'm designing an API controller, and since the best way to do this is to use the KP and KI coefficients, and I can also tell the symbolic engine behind the scenes that these are basically not complex values, these are real values, because if I have a controller, an API controller, my coefficients should be applicable to the real world. So basically I need real values so I can tell the symbolic engine. Now I have the controller structure, which I know. By the way, there are different ways to implement a controller design. So we can code it differently. I will mention that in a moment. But first of all, let's look at the settling time specification. We have a 1.8 settling time specification, 1.8 seconds, and we have also 0.3 rise time. Okay, so maybe I can push this down and I can put this up here. Now, looking at these rise time and settling time specifications, it might be a little troublesome because both are depending on zeta and omega n. There are some certain formulas for this. So, if you don't remember, let me remind you that the rise time can be calculated via the following formula. You can use pi minus beta divided by omega d. So you have to remember that we have zeta and omega n, but these are represented basically in Cartesian coordinates. And if you are looking for the same representation in polar coordinates, then you will see that your point has a gain or a distance to the origin of omega d, which basically also is defined as follows. It's the square root of 1 minus theta square times omega n. And you can acquire this by remembering that the real value was zeta times omega n, and plus and minus it depends on 1 minus zeta squared omega n I. So we define this part as the omega d value, as you can see, and this is the zeta omega n. This is the imaginary part, this is the real part. If you take both squares, you will see that zeta square omega n square plus 1 minus zeta square omega n square will be the end result, and you will see that, let's take it a step further, we have omega n square minus zeta square omega n square, and you can see that these terms cancel out, so we have only omega n square. And since we are looking for the absolute value, or the distance between the dominant pole and the origin, we have basically omega n. So in polar coordinates, you will have a distance of omega n, the origin, and then there will be an angle. And this angle can be calculated by using the tangent beta, which is the same beta as this one. So this tangent is equal to the imaginary part, which I've already written down, which is this one, and the real part here. So you can see that omega n will cancel out. You will have square root of 1 minus theta square divided by zeta. So it's only depending on zeta. So then you can see that there is a relation, since this is the square root of 1 minus theta square times omega n, and this is relating to zeta. So this is a function of zeta and omega n. This is the settling time is also a function of zeta and omega n. So you might use some pen and paper to work out what or how you can basically solve zeta and omega n. But as you can see, if you are not given an overshoot value, which is directly related to the zeta value here, as in this case, you might end up in a pre-processing problem that needs to be taken care of. Now, how can we basically get rid of this? There's also a different formula for this, which makes things much easier. And as far as I remember, there are two different formulas, but I will give you the simple one. There's also a second order formula. This is the first order formula. You can use 2.5 times zeta plus 0.8, and you can divide this whole thing into omega n. So this is the relation there. So you can use whichever you want, it depends on you, but they will give almost the same result. You can check it later. We also know that our settling time is 4 divided by zeta times omega n. So we have basically two formulas. So you can work out omega n in both. That will give you the following problem here that I'm going to state. And from this formula, when I copy and paste it, I can just take omega n, and this can go here, and repeating the same procedure here will give me omega n and ts. Now the only thing that remains here is to equate them. So I can just do this here. Now, in order to simplify things, I might divide everything by TR. So it will look like this. And I can multiply with zeta here, which will give me even a better equation here. This will be zeta squared, and this will have zeta in it. So since I have TR on both sides, I might multiply this with TR. That will give me 4 times TR divided by TS here. So maybe this is a thing. And then I can also put in a minus sign here, and this is equal to 0. Now, if you remember, I can use the roots function, and I can give it 2.5, 0.8, and then minus 4 times TR divided by TS. So this should give me a solution of this, which then will eventually give me or the positive value, and probably the value that is between 0 and 1 would give me zeta, because that's the only solution that I am interested in. If I have complex values or certain other things, then you might reconsider your equations. There might be an error, or the settling time and rise time may not be compatible with each other. So and that's that. Let's see what the result basically is. Let's save S11. So if you think about it, this is challenging in a way that you need to first work on these two specifications to acquire zeta and omega n, and then you are starting the problem solution. So basically, I am not interested in the negative value that is the solution of this equation or polynomial. So I'm interested in the positive one. How can I acquire the positive one? Well, basically, I can do this here, and I can use MATLAB, or I might also do it like this, and zeta. So I'm going to write it down, but you can think about it or look for it. If I use a zeta greater than 0, what MATLAB will do in the background is it will give me one logical 1 if the specific element is satisfying it, and it will give me a logical 0 if it's not. So I will end up with an array that has ones and zeros based on the fact that if the condition is satisfied or not. So if it's a positive value, I will get a 1, and if it's not, I will get a 0. So, and sending that with the parentheses to the zeta will then eliminate those values that are logical 0. So I will end up with the only value that will satisfy this condition. And based on that, I can now see what zeta will be. So let us write down and check it if it's working. So I've acquired, and I've automatically acquired. It's the important part here. You might take your calculator with you and just try it your own, or you might use a pen and paper to work out things. But the best way here is to automatize stuff in order to being able to change, let's say, the settling time, the rise time, and see the effects. So what I'm trying to do, or what I'm trying to stick with, is that if I'm writing a code, it should be written so that if I change something, it should adapt automatically. So now I have zeta. I can use both formulas again, but I would say that this formula, the settling time formula, is a little bit more handy than the other one. So at this point, I'm basically at a point where it doesn't matter if I had the overshoot or the rise time and settling time together. So at this point I know zeta, so everything will be pretty much the same. 4 divided by zeta times Ts. So that will give me omega m. Now I can construct PDS, which is s squared. And by the way, I know both values, which means that I am aware of the exact point that I'm trying to satisfy for a polynomial. So I know basically my poles numerically. So even though I'm using the symbolic toolbox because I'm going to use them for the coefficient for the problem that will be based on the coefficient equations, so the algebraic method basically. Now I have this here, so I might get rid of this here, so it is a little bit tidy. Now, was it possible to use pi minus beta divided by omega d? Of course, but it will require a little bit more than a roots implementation, but it's also possible to work that out, and maybe it's a good idea for you to try it on your own, to try to use the other formula too, so you know the alternative version basically. Now, since I have my system defined here, I have my dominant pole pair, I have my controller definition, I might go ahead and define my problem, or I might go ahead and look for the feedback structure and calculate my transfer function. So, using num then, I can get TSS, and then we have num and done. Let's look at that. Maybe I should also use let S in order to have a nice representation. So the numerator and the denominator are given as follows, and you can see that I have linearly dependent coefficients, which is a good idea. If I would have defined my controller in terms of k, the gain, and the 0 z, I would have some multiplications of unknowns in the coefficients, which is not that desirable. So I can directly see what the relationship is, and I can maybe predict or even try to solve it by just looking at it with a naked eye. Now, you can see that my PDS is x squared, so a second order polynomial. I have a third order closed loop polynomial, so I need to add another pole, which is also a real value because it's just one pole. And my PDS is s plus p. And then I can state my problem. I can say that the problem is to get the coefficients of my denominator. I need all the S coefficients, and remember that if you don't use these arguments here, it might use any symbolic variable. If I had, and in this case I have KP and KI, it might try to get these coefficients instead of the S coefficients. And if I don't pass the parameter all, it might skip those which are not available here. For example, if I have S plus the constant term, it might not give me this one, so I might end up with 1, 2, 3 coefficients, and then my PDS has 3 coefficients, and I'm trying to equate them and get the problem, but that's not the problem that I'm looking for, and it would be cause a problem because my results will not the same, or my design will not be valid. So then the coefficients of PDS times PDS and all S-con coefficients are needed here. And let's use a small for loop to look at my equations. It's always a good idea to look for the equations because before you try to solve it, you see exactly what's happening, and it is always a good idea to check the problem. You might have some typos, you might have some logical errors, so okay, maybe the ith element will be a good idea. There we go. Now I can directly evaluate the value of p. It's 10.66 or something like that, maybe 556, I don't know, or yeah, you get the idea. I can approximate the value of p. Since I know p, I can multiply this and see what ki should be, and then I know ki, so I know again p, so this gives me the value, extract 20 from it, and you will get kp. So even without MATLAB, it's pretty much easier to look and solve. By the way, if we can skip the second one, if you've just validated that the first equation is a true statement, you can just skip that in order to focus on the real problem here with non-trivial equations. And you can see that I have a unknown p, kp, and ki, 3 unknowns and 3 equations, so there's just one solution. And that solution can be provided from MATLAB. So let's say solve, and then let's give it the problem, and then I will look at the solution here. So I have 3 parameters, so maybe sol.kp, sol.ki, and sol.p should give me the values that I'm looking for. And you can see I have certain values. Let's define some placeholders, kp for kp value, and then double, and then this here. So this is basically converting the results from symbolic into numeric value. So this is ki, and then I will have pv, then this here. So kpv, kiv, and pv are my unknowns here. So I can see now that I have a certain value for kp, ki, and my pole here, resistive pole, is at 10.55. Now I can check what zeta times omega n was, and it was 2.22. So there's almost a 5 times factor, which is called basically the dominance factor, and it's not bad. It should work very well, because the further away residue poles and the zeros of this closed loop system are, the better the response will be, or the more will the whole closed loop system response tend to the second order dominant part. So it's not a bad design, but I don't know where my zero is, but I can evaluate that also by looking at this. I have 1.5s plus 9, which is 3 or 4, something like that. It should be on the left, so it should be not so bad result here. That's enough with the comments. Maybe I should go ahead and use these values and define my controller. I can get the exact results that I'm looking for. Then I will use feedback here, and I can just take fs times ts comma 1, and then let's say let's look at ps here first of all. And I might just skip this problem, and let's see what it looks like. There we go, but a better idea is to use the setbk k, because I want to look for the zeros, poles, and gain. Now you can see that it is at approximately 6, and I have a pole at 10, so at 2.22, not bad. It should give us a reasonable result, so maybe we should look at this result here. So let's have TS here. Well, not bad. And remember that I was not looking for overshoot, I was looking for rise time and the settling time. So let's remember what those values were. Settling time was 1.8 seems to be alright. Rise time was 0.3, seems to be alright because here's 0.5, so you have a pretty good response here. If you're interested in the exact values, you might use step info, which will give you the experimental details of the specifications. And you can see that the rise time is 0.19, so 0.2. I was looking for 0.3, not bad. And then there's a second time of 1.82, which is almost the exact value here. So not bad for a design. It's even faster than I've tried to design, and that might be the effect of the zero. And that's it, basically. Now we've accomplished the first task that we were given. So we have designed the controller itself. Now we are interested in the control signal, and in order to get that, let's examine the feedback structure. Therefore, you need to look at the feedback structure, and let me quickly try to explain you what it looks like. So we have the structure here, and then we will have a feedback here. So somewhere around here. So now this is the output Y, and I have a reference here R, and then somewhere here, or basically here, we have the error, the control signal here, and then Y, and this Y is measured, and R minus Y is equal to E times Fs gives U times Cs gives Y. So if I'm trying to get the closed loop transfer function, I'm basically using this feed-forward path Fs times Gs divided by 1 plus Fs times Gs, because this is how the closed loop transfer function is calculated. And you can use these relations, E equals R minus Y, Fs times E gives U, Gs times U gives Y, and again here's Y, by substituting values and eliminating the signals E, U here, you can get the same result between R and Y for the transfer function. So you can work it out basically, and it will give you Fs times Cs divided by 1 plus Fs times Cs, because this is negative here. Now, what if my output is not Y, but my output is U? So if I'm trying to examine the control effort or control input here, basically the controller output, but the system input in this case, I might take this transfer function here and this Y and define this as an output, because I'm interested in that. So I then have to basically place this into the feedback path, because at this point I should reach Y. So in order to be able to subtract R and Y, I need to have Y, and my U is fed back. So basically my GS should be placed in the feedback path in order to get this error and then being able to generate this U. Now there's another version where I might also be interested in the error signal here, which might be the case. So basically this time this goes into the feedback path. So I'm taking it away. This becomes the output, and somewhere here should be Fs, because now I am feeding back. Sorry, I'm feeding back my error. So my error should be multiplied with or applied to the controller. The controller should give me the control input or the input of the system, controller output. That should be applied to the system, and then the system should give me Y, and then I have R minus Y, which gives E. So these three connections are very essential, and if you know these, you are a little bit more aware of the error, the control, the effort or signal, and then also the output. So we're used to this one, but these may be new for you. So think about this. You might use Simulink to try this out, because it will give you basically the control effort, and the error. So how can I get this closed loop transfer function? Because the transfer function has an input and an output, and if I choose R as an input and U as my output, I have to evaluate my transfer function. So let me call this TS, let's say U, because it's relating to the output U, and I always know that my input is a reference, so TSRU can be the case, but I will just use U here. So I have FS in the feed forward path, which means that I might use again the feedback, but the feedback command. But I have FS in the feed forward path, and GS is in the feedback path. So basically, most of the time I write FS times GS and 1 here. That means that FS times GS is in the feed forward path, and I have 1 in the feedback path. Now things changed, and I have FS in the feed forward, GS in the feedback. Now I can also adjust my transfer function so that I have 1 in the feed forward path because there's no transfer function and there's 1, and FS times GS is in the feedback path. So these 3 transfer functions, and this relates to E because I might also call this TSY here. This is relating to the output. This gives me the output. If I'm applying a step to this, I will give a reference of step and I will look for the output Y. If I'm applying a step to this, I will apply a step as a reference and I will see what the control effort is. And the same is also for this here. If I apply a step signal, I will get the step response and it will show me what the error is, how the error changes. Now let's get rid of these representations here. Now I have to find 3 different transfer functions and I will have 3 different results here. So let's first of all try to Y and T here. So I should give it a T because I have setting time of 2. It might be reasonable to use the following as the time signal. And then I have 3 here. So let's give it as a time vector. And this should give me the output itself. I will have the control output and the error output here. Or you might also skip those and define them as U and E. It might be a better idea. Now let's have TSU and TSE. And then I will do a subplot here. A 3 row, 1 column, and the first one is this plot here. So I might skip these T's, and if you don't want to define a parameter, but you have to, you might use the tilde here in order to bypass those definitions because T doesn't change and I will get back the same one. It's not a big deal, but you might want to do that. Let's prepare a plot here. This is basically the output here. X label, x-axis here is time in seconds, and I have y label as yt because it's the output, and let's show the value. And I will repeat it for my control signals. So basically I'm using U, this will be UT, and this will be U, or control effort, or whatever you want to use here. And then I might go ahead and change it to E because I will also see the error here. And that's, I guess, should be E. That's, I guess, it. So I can run it, and I get the result here. Now, let's look a little bit closer to this see now that I have the following step response, and I can also see that my control signal starts with 1.5. It goes up, it goes down to 0. At this point, it crossed the reference, so it was almost there, but then it did go far away, so further than the reference. So at this point, the system tries to compensate for that and applies a little bit more, and it repeats in a certain path, but there's a damping here and not the high damping. So this oscillation here appears, and I can also see that at a certain point my error crossed 0. This means that I have crossed 1 here, and I can see that here, but it was not enough and I didn't stop there. I did go a little bit further than needed. So at that point I tried to cross 0 again, and I did it again, but this time I was still not able to stop at that point, but I'm in the vicinity, so I did increase my control signal, and my error decreased at a certain point, but after the crossing it still was too much. So basically I'm trying to settle down, but I'm applying a little bit too much in terms of control signal, because if I would have stopped somewhere here, I might have ended up stopping at the right position, but that's depending on the control parameters that you use. Because you have an API controller, you have an integral part and a proportional part, so this means that if I would have had a p-type controller, these two graphics should have been in the same shape. Maybe the values would have been different, but there would have been also the same relation, namely the controller gain. So if I had this and I had the gain here, so basically everything here with the same shape would be here, but 2 times the values of this would be in the case of the p-type controller would be 2. So since I have also the integral part, it is not only constructed using this error here, but the integral of this error will also be used, and a linear combination of both, which is the PI controller itself, will generating the control input. And this control input is applied to the system. So basically what we are trying to do with the controllers is to design or choose these linear combinations in a good way or a wise way, so that I have the perfect output that I have in my mind. So that I'm trying to achieve here. So now I have also uh, uh, basically we have also accomplished the second task, but we are not quite there, because we can see in the third task here I need to limit control signal. So I have two options here. One is to use symlink, so I can implement this limitation, because I need to place a nonlinear element or a separation element that is between the fs and gs. And it's not possible to use LSIM or step in that case, because you are not able to give anything else than transfer functions, and we are not able to model this as a transfer function. This is a static nonlinear element or piecewise continuous linear element that changes the behavior of the control signal. So one way is to use Simulink, and that's the easy way. You might go ahead and open Simulink and stop this video and try to implement this. You know what the controller parameters are, you know the system, you place them, and between fs and gs you can place a saturation element. If you double click that saturation element, you are able to do it in a lower bound and an upper bound. So just typing in these values and a feedback structure, you can apply a step, and then you will see the true output and everything will be alright. But here we will try to implement this using only code, and therefore we might use a little bit of the control theory and some coding tactics. Now, we know that basically a linear system, we know that if we have a transfer function, we might change this into the space representation. And we can also use a discretization so that we have a discrete model. And if you have a discrete model in order to code some simulations, you have to have a discrete model, a discrete space system basically, because instead of differential equations, there will be difference equations. And using the for loop and some structures, some vectors, you can implement any system that is linear. So this is the trick that we will use now. And therefore, we have to change this so that we have a state space representation and then a discrete state space representation, and we will try to implement that. Now, let's open up our code here, our editor. Let's copy this and let's paste it and let's save it as run2 because I will change stuff and we will go back and forth in order to compare if I did implement it or if I was not able to implement it. So basically up to this point I can just keep it, and maybe this point will be necessary after I'm done, so I can get rid of this here. So I was able to use these here, but I will not be able to use this anymore. And the only thing that I need is I don't need all the transfer functions or anything else. Those are not necessary anymore. I just need the system, the controller, and then I will implement it in state space here. So how can I accomplish that? Basically, first of all, I can use tf to ss, which is a function included in the control system toolbox. That means, as far as I remember, the numerator and the denominator of the system, and it will give you A, B, C, D. So it should give me something like this. So if you're not sure, you might go to the console and type in doc and tf2ss, and it will give you the documentation of that. Or you might also type help if you want help. But as you can see, you can give the numerator and denominator, and it will provide you the corresponding state space matrix. So if you're not familiar with state space realizations, you might check out YouTube or you might check out my videos. There should be one with that. But the only thing that you should know is that ax plus bu equals x dot and y is equal to cx plus du. So you will implement it and you will see, and the only necessary information for this is that. How can I get the numerator and denominator? So that's a question that I might face here, or a problem. So I will use gs here. So you should type numerator and then the same for denominator. Now I will explain why we have to use some interesting parentheses here. So basically we are working with systems, but that might not be the case for all, and you can see basically the representation here. So in those cases it will give you an array of numerators and denominators, but since we're not interested in that and we have only one numerator and denominator, we don't need these arrays. We should just extract the value that is there, because it will give us the numerator and the denominator directly. Now at this point, let's look what A, B, C, and D look like. And you can see that it is a 2 by 2 matrix here. So I will directly use these definitions. But I have to use the discrete version because I will not use any ODE solvers. If you know a little bit, let me explain to you using Simulink. In Simulink, if you remember, you are dragging and dropping some blocks and connecting them. And if you hit one, you can see in the bottom that there is a solver defined. And this solver is basically a differential equation solver. You can use ODE solvers there, 4, 3, 2, 1, maybe also 5. There are some algorithms that are capable of solving differential equations. For example, Random Kutta or other algorithms. So if you are working in continuous time, you have to use one of those solvers. And I might use that as a possibility. You can code ODE, and that's also possible. But since I am interested in separation element, and since I want to code my own, I will use the discrete version here. So that's the reason why I am not using ODE. It looks a little bit simpler in my opinion. I don't know. Now, for that, I will use zero order hold. You can also use C to D here, but I will just implement it myself. The A discrete version here will be identity times plus tau, which is the sampling time, times A, and I will explain you in a minute why that is the case. So we will get rid of this. I don't remember if I explained it in my notes. Hopefully I did. If I did, I will show it to you right now. Now, let's go on. Now the C discrete is C and D discrete is D. Nothing changed. Before I explain everything, let me just guide you through the whole code. Now I need a state vector because x dot equals ax plus bu. So x is needed. I need u. It's also needed. And then I will also need y because that's my output. Maybe I need also an error reference. I will come to that. Now, what should be my state matrix or vector be? So before I do that, I have to also define my time vector. Let me define my time vector so that it is basically a small vector that we can keep track of. Now I have 0, let's start from 0, I have 0, 0 0.1, 0 0.2, and 0 0.3. These are the 4 values. And now the data structure in X is basically a 2 by 1 vector because I have a 2 by 2 system. So for example, it should be 1, 0 at a certain time instant, and it might become 2, 1, and then it might also become 3, 3. It depends on that, but I want to use it as follows. I want to say that this is the first time instant, since we are in MATLAB, I should use this here. So if t1, so basically if time is 0, I should have 1 and 0, which means initial conditions. And then if the next time sample is there, I might have 2 by 1, and then the next time sample here should be 3, 3, and we have T4 here, probably, and we will have, let's say, 3 and 3 again. So I will use this structure, so this is X here, because I need a 2 by 1 vector for every time instant. This means that I need 4 columns in this case, and then 2 rows. So how can I do that? Well, basically I can say 2 by 4. Or I might also get this information using size A, and you can use max or min to eliminate just one of the values because they are equal. I can get the degree of the system, which is n. And I might also use the length of t. So because this is 2, I know that it is 2. And since I have 4 elements in my time vector, I'm using the time vector length. I can define this here. Now I know that I have for every time instant a n by 1 vector, which then builds or which then constructs a matrix that has n rows and length t columns, which correspond to every time instance given in this vector here. So I have a scalar for the control input. So it will be for ultimate, let's say it looks like this here. I will have 0 at all time instances. So this means that I will have a 1 here, and I can also automatically get this information by looking at the matrix. But I will leave it here because we are working with single and output systems. In many cases, this might be changing depending on the B-vec or B-matrix. So the columns will be always length t because I need for every time instant I need to store a value here. And the same will be for my output because I know that. Now, if this is my output and if I am able to subtract the reference and the error, it means that my reference and my error should have the same structure because at every time instant I will be subtracting them from each other. Then let us define the integral of the error as q. I use q, you can use anything else, but I use q here. So this will store the integral of e at every time instant, and I will use this to build the control over here. So basically, it will be a linear combination of e and q in order to get u, and I will use x dot equals ax plus bu in order to get all x's at time instance, and y equals cx times du, a linear combination of x and u, you will also get the output. If you have the output, you can take r and y and take the difference, and you will get e. Now it will repeat like that over and over again. So how will I construct the 4? Well, I will start with I equals, let's say, 2 here, and I will come to that in a minute. And let's have length t. So why did I not put in 1? Because I am using difference equations. It depends on the previous value. And if I start with 1, what will be the previous value? There is no previous value. So if I start with 2, the previous index or the time instance before will be 1. If I'm at time instance sample 3, I will go back to sample 3 because I need the previous values in order to implement this. And let me show you the structure of my difference equation. It looks like this, a little bit more general than this, but we will come to that. So I'm at time instant k, and I have a xk times b uk here. So this is my basic equation, the equation of evolution here. I use previous values, the time instant k, and I'm calculating the next state from that. And I'm using this basically in this format here, and I'm getting rid of this. I will use C and D in order to calculate the output. And if I have that, my error can be calculated using RK minus YK here. And if I have that, I will somehow, I will skip this for a second, I will somehow use QK and EK in order to take the integral. Somehow I will accomplish that, and once I'm done with that, I will go ahead and calculate my my control signal, which will then be KPV times EK here, because it's the proportional part here, and then I will use KIV here times QK, which will be the integrator part. And once I'm done with that, my UK will be applied to the system. So the ordering here is very important. And if you think about it, I would have a initial value for my reference, and I need an initial value using these here. So you can see that there's UK involved here. So it might be seeming a little bit not problematic, but the first step here is to calculate basically the output. I'm starting at the output because I have initial values for this. I assume that I know the initial values. So I will calculate this here. And after that, since I have the output required, using the initial values of the controller and X, where the controller should have 0 as initial value, I will have the output. Once I have the output, so I'm basically at the output of the whole structure, I am feeding it back and looking for the initial value of the output and the reference signal. And I construct the error. Once I have the error, I will go ahead and calculate the integral. And if I have the integral, I will go ahead and calculate the control signal. Once I have the control signal, my first state or my first time instance value using the initial values will be constructed. At this point, I will use xk plus 1. Now, if I have done this one here, my k will be increased automatically because I'm using 4. It will then give me yk plus 1, but I will denote it with k because it will be the previous value at that time instance. So then this will start over. So this is basically how the code will look like somehow, and I need to change it a little bit. Since I have, let's say, since I have defined I have to use, instead of k, I have to use I minus 1 because this is the previous state. K is the previous instance here. So, by the way, these are D because I'm using discrete here. So this is dd times uk, and k is I minus 1. So everything should be I minus 1 here. Every k should be I minus 1. Since I have k plus 1 here, if I paste this, these will cancel out and this will be xi. So if I is equal to 2, you can see that y1 is equal to cd times x1 plus dd times u1. And then e1 is equal to r1 minus y1. And then q1 is somehow calculated here. Let me paste that there too. And this is somehow calculated. And then I will use qi minus 1 times kiv plus ei minus 1 times kpv to construct ui minus 1. And this ui minus 1 will be then multiplied with bd plus xi minus 1 times 80, then generates my xi, which is basically x2 here. Everything here is 1 as an index, and this should be x2. Since this was x2 and I will be increased here, I will start with 2 basically. So or basically it should be 3 because I started with 2. This will use y2 equals cd times x2 plus dd times u2, and then e2 equals r2 minus y2, and q2 is calculated. Then I will have u2 calculated from these values, then x3 will be calculated, and this goes on up to the point where I am at the end of my time vector. So how can I calculate my integral here? Now, let's start with a derivative. Let's say we have x, and we are trying to calculate this derivative here. And let's say we have ax plus bu here. Let me explain it. Now, you can go ahead and use delta x divided by delta t as an approximation, which is corresponding to the first order, which is corresponding to the zero order Holt method. Now, delta x means that I can use the x difference from time instant to time instant, and I can also use this delta t, which is basically the difference between two time instances, and I can use that for an approximation of the derivative. That's the basic idea here. This delta x can be calculated using xi minus 1. This is the backwards difference. Keep that in mind. Now the same operation can be done for t, which means that is ti minus ti minus 1. Now I know that my time instances occur discretely, and the difference between them, as defined in line 38, is 0.1, because I have a t vector, and if I look for this t vector, which is not available at the moment, if I look at this t vector, I can see that the difference between any two time instances are 0.1. So basically this is tau here. This is the sampling time. I can get the sampling time like that. Now, since I have defined my time vector, this time vector should be available somewhere here in order to define tau, which is t2 minus t1. You can use any two consecutive time instances, but I will use this one, so tau is defined and I can calculate this. So here I can also use tau instead of this difference, because this is delta t. Now this will be at the I minus 1 index and the u I minus 1. So at this point I might multiply everything with tau. This will give me tau times a and tau times b. Now the only thing that's left is to work out this relation. Just go one step further. This will be the equation looks like this at the end. Now I have used the definition of derivative, the geometrical interpretation basically, which means that the difference divided by the other difference, the time difference, gives me the approximate value of the derivative. But there's only one important point to note, that is that I should choose tau wisely and as small as possible, because if this tau and time, which is the time instance difference, if this is not small enough, then the derivative will not be valid, or this relation will not be available. So we will see that in a moment. Now I can see that I have the same here, xi minus 1 here. If I use a parentheses, if I factor it out, I will see that there will be a identity matrix here. And this is the reason why I used this identity plus tau times a, because this is basically this AD here, and this is BD, and tau times B gives me BD. And since I can write static equations as they are, yi is the same as cxi minus 1 plus the ui minus 1. The relation is the same, so you can just take these as discrete values. This is the order holds. So if I, let's say, define d2 divided by dt equals e, if you work this out, it will give me 2 equals e dt integral. So this is an integral basically. So how can I do this? Basically, I will use the same here. I will say that 2i minus 1 or 2i minus qi minus 1 and divided by tau equals ei minus 1. So times tau will give me this here, and if I arrange this, it will be this one here. So this is basically the numeric integral, and I will paste here. This is how I can calculate my discrete integral. Now at this point, I have to keep in mind that x is not a vector, but a matrix. So I need the I minus 1th column, because the time instants are related to the columns. So I need all the rows, but the I minus 1th elements in the column, because that's the time instant that I'm looking for. I don't need to do the same for ui minus 1, because u is a vector. It's just one element in if I'm looking for the rows. And in ri minus 1, it's the same. Yi minus 1 again. Qi is a signal that is just of length 1, so I don't also need to do that. My error is the same. I need a tau here. I have that defined also, so I can leave it at that. And then there's ui minus 1, which is kp I minus 1e is scalar 2. So wherever I have a scalar or a vector basically with 1, 1, 1, 1, I will not touch them, but if I have a matrix X or if there's a expression of X, I have to use the colon, comma notation because I need all the rows but the I minus 1 column, and this needs to be like shown here. So at this point I should be able to look for my result here. Hopefully it works. I have 0, 0, 0. Now the reason for that is that my reference is 0, because you can see that it is 0. So I have to change it to once in order to start with a reference value of 1. Now we can see that we have different values, and it tries to evolve so that these will be generated here. Let's basically try to look for my output and see what happens. My output looks like this here, so it needs some time. What about the true vector here? I am somehow calculating my integral, and you can see that I have an error of 1, but my sampling time is 0.01, 0.1, and the error times delta t is 0.1, so it seems to be working. In order to be sure, we should now open up this here. I have the same y, same u, and same b. And if I increase the time here, I should be able to do that. But before I do it, let's see what happens here. Did I have an error? No, and I can see it's a triangulated version. That's because I need to increase my sampling time and my time vector. So it stops at point here. Now, let's do that basically. Let's increase our time here. Now I can use 3 seconds and 0.01, a finer gridding, and you can see that I have basically the same structure here. It looks the same. Only problem here is that I have these last elements. They are dropping down to 0, and that's not the case for E, because E will be calculated here, but since there's no other loop that calculates Y here, I have a problem there, or basically U is not calculated. Q is not even available, but if I would have plotted Q, I think it should be the same, or maybe not because it reaches the end value here. So these are dynamic equations, and those dynamic equations are setting the last values. But if I don't have a dynamic equation, or if I don't have the information available, they will drop down to 0 because there's just one element missing. So how can I solve this? Well, basically, I look here for y, and is that u? It is ut. So for y, I might go ahead and calculate the last element here based on the last element of that, and based on the last control signal here. If I run it back again, I can see now that I have solved this yt here, but still I have a problem with that. Maybe for the control signal I will have an error available. My integrator, I'm not sure about that. Let's try this out. Let's say for the end values, calculate the error and solve that too. So now I can also look for the internal signals. This is an advantage that I was talking about and that we needed here, because if I cannot reach the internals, I will not be able to restrict my control signal with a certain nonlinear element. Now at this point, let me generate a 4x1 plot here, so I can include my integrator. So this should be Q, this should be Q, this should be Q, and this is basically the integrator. Now I will see what the output of the integrator part of my controller is. And you can see now it starts with a 0, it takes an integral, it has a certain area. This area is basically calculated using this here. Once it reaches the point, the maximum or the area has a certain value. At that point, it starts again to increase, and then my area will be calculated. So using this and this, the linear combination gives me this. And you can see that at certain times it looks like the error, certain times it kind of looks like the integrated part, and that's the whole idea behind this. So I have plotted now everything. The only difference here, if you will use Simulink, will be that your step will most probably start at time instant 1. And if you're wise enough, you might also, or if you have some coding experience, you might also be able to emulate that by changing your reference signal here. So what I like to do, and I will show you what I like to do, is I like to generate my signal using zeros and ones here. Now, the size of my first part will be, it should start with 0, and it will have this sampling, or did I have tau? I have tau, so this is a better idea. And the ending point is 1 second, so basically I will have a 0 vector that starts at 0 and will stop at 1 second, and I will then start with 1, I will have an increment of tau, and my last value will be the same as the time instant here. So if I have to add 1 plus tau because this is the last sample and the next sample starts at 1.01, so I should add a tau in order to have the same size as the other ones. If a size mismatch will happen, then you will get an error. And you can see now that my reference starts at 1, so I have pushed my response to a certain point. And it jumps from 0 to 1 because suddenly a reference is applied. I might also want to plot my reference signal here with a color. Okay, if I do this, this color will most probably change, and it did, but I cannot. Okay, that. If I change it, I can see now that I have the reference applied. The only problem is that my color changed. So in order to prevent that, I might provide a blue color as a parameter. So if I pass that, and that. So it should be with the same blue color. I have the reference, the output. So if I have this, I might want to increase my time to 5. Let's say 5 is a good idea. Everything settles down. Now I can see the effect. If I have a sudden step function, if it's applied at the first instance, and you can see that this is not a Heaviside function, it is more like a ramp function, but it does the job. By the way, plot may be not the right choice here, because you might used to use stairs, and the reason for that is that we are in discrete time, so the more correct version would be this one here, because it has no value between 108 and 109. But if you use, let's say, Simulink, it will have a continuous jump from there to there. But since in the digital world, it's not a big deal to use the discrete version. Only thing that you should be aware and be careful about is that maybe discretization methods may play an important role, but since we are interested in separation, it's not that big of a deal. But if you are working frequently frequency dependent, then this method might not be for you because it might mess up the frequency aspect of your simulation. No, that's that. Um, Now, since we have this, I am going to copy this and I will paste it here. I will not change anything other than the saturation. Now I'm able to add some saturation to my simulation here. Now how can I do that? Well, basically I will use another vector of the same kind, but this time I will have U and U set. So this is the output of the saturation element, and this is the input of the saturation element. Now, at this point, once I have calculated my control input that is ready to be applied to the system, I will go ahead and look for my value here. And if the value of the control signal that I've calculated is bigger than 0.7, then I will have to use something else. And if it is less than minus 0.7, okay, this is the lower bound, then I will do something else. And if those are not the case, I'm just free to use my control signal. So before I do something here, I can see that basically I'm equating those signals. If no limitation is happening, then my U and my U set will be the same. So basically, I will go ahead and apply this to the system. The saturation output will be the input of the system. So if there's no saturation, then the control signal will be directly applied because U set is equal to this, and this is equal to U set. This means that this will be here. So this will be U. And that was the case before. And you can see that this is U. I calculate U and I apply it directly. But if there is some saturation, if I'm not in the linear region of the saturation, if I'm at the bounds of the saturation, then my U set I minus 1 should be equal to the upper limit, and that's it. Now, it doesn't mean anything that I have a control signal, because the upper limit is the limit, and I can only apply that value to the system. No higher value is allowed here. If I have U equals, if my controller produces a control signal of 0.8, then I'm not, unfortunately, I'm not able to apply that to the system. I can only apply 0.7, and that's it. And for the lower limit, the same applies there. And keep in mind that I'm not setting U, because for debugging reasons, I want to look for the raw control signal and the modified control signal. And that's the reason why I have U and U set separately. Now, hopefully, if I am not wrong, it should give me a nice plot here, and I will look for the raw data, which is black, and the colored data is the new data. Let's see what happens. Now you can see something happened there, but these legends are in my way. I might put them on the left. Therefore, there's a code. You can just say that the location should be, let's say, west. I guess it would be a good idea. If I pass these two parameters here, then my legends will move from the right to the left. And if I maximize my window, I have a nice clean look here. So since I have used a step function that starts at a certain point, I can just assure myself now that I can see everything. Now I might also want to put in this U set here. And once that's done, I have this nice window where I can see what happens. Now, this is my response, and that was not the case. And you can see that at a certain point, I reach the reference value, but my controller somehow has touched the limit, or it even starts with the limited value here, and this limit, even though I have reached the value, is still applied. So if you think about it, if I'm at the reference, my error signal is not that high, and you can see that here. It's in fact almost zero or around the vicinity, but my control signal is very high, and my raw control signal, which is black, at this point has a peak which is between 3 and 4. So it's 3.7 approximately at this point. So why does this happen? Why do I have this sort of behavior? And once I'm past the reference at a certain point, my controller then settles down, it decreases its value, and then it enters the limit again, and it is below the limit, and I can see now that it calculated my corresponding control signal that eventually settles my response to the reference value. Now, this bump here is basically the problem, because at this point I should have a decreasing integral, or it should not take that much time to, let's say, dissipate this energy in the integrator, stored in the integrator. Now, this is called the wind-up of the integrator. So basically what happens is that my controller panics if it hits the if it hits the upper bound, or even in the case of lower bound. Now, what happens is that it is not aware that it is basically reaching the reference. Why that is basically because we hit this point here. If I had applied the original control signal, the error should have become much lower. But since I am at the limit that I can apply, and since I'm applying a lower value, my controller becomes more aggressive, because it thought that it would correct its output so that it would become near the reference. So it takes quite some time for the controller to realize that there was a limit, and this limit was preventing me from applying a high control signal, and this high control signal was not applied. So if that's not applied, then the system is far away or further away from the expectation of the controller. So what the problem is basically is that if I have an integral, at this point my error decreases, but my integral still increases, even though my error decreases. So it's basically not the same data here, because the integral of this should not look like this. So it's not the right error. So the integrator is not aware of the saturation, because it takes the integral of this area here. It takes this into account, because you can see that it increases at a certain point, and since the error becomes negative, the integral becomes lower. But it's not due to this error, but this control signal, but this error. So basically, there's a problem, and this windup causes some problem. How can I overcome that this windup? Basically, there are two methods to this. You can switch off the integrator during the saturation. So if you're in the saturation area, you might just switch off the controller, and that's it. much better response. So we have to switch this off. Or the other method is to feed the difference between the applied and the actual control signal, and or the raw control signal, or the control signal generated by the controller, and the saturated control signal, because that difference is used during the integral. So adjusting the value, the integrator should have a better or a more accurate integer signal. So let's copy this. Let's paste it in here, and let's call this one 4. It's hard to explain it, so maybe I should just demonstrate it. That might be a better idea. Now, if I want to overcome the problem here, I should look at this point here. Now, I have U set and U, and they will be different if I have saturation. You can see that. If they're not in the saturation region, if they're in the linear region, then I have basically no difference at all at that time instance. So maybe as an IT wind-up strategy, I should go ahead and add the U set here, I minus 1, and subtract my control signal. So as I've mentioned before, this will be 0 if we are in the linear region, and this will become most probably negative if I have some saturation limit, because this will add 0.7 here if I'm at the upper limit, and it subtracts the control signal that we've used and that we wanted to apply here. So if I'm not wrong, this should change the behavior. But before I run this, let's call this figure 2, and let's go ahead and run this, so I can go ahead and compare this. Let's see if there's a difference, or if I was not able to implement it at all. Now the issue here is that I am basically I didn't generate this U value, I guess. So that might be the problem here. Because I'm calculating it here. This might mean that I need to use even one sample. So this might mean that I need to use an if statement here, and if I is greater than 3, so else and. Now, if I'm able to go 2 samples behind, that's basically the reason why I'm using 3. If it's greater than 3, let's take 4, then I'm able to go 2 samples back. 4 minus 2 will give me the second one. But if data is not available, if I'm at the first sample, I cannot go back even 1 sample. If I'm at the third one, that means that I'm at the second sample. I'm still not able to go 2 samples back. So I need to put this in here. So let's do this instead of that. And for the other case, let's just get rid of this whole adjusting term here. So this should work. If not, I might think about it a little bit more. Now, what's the problem? Must be plus 4 integers. I minus if I is greater than if I is less than, let's say that, because I was trying to prevent exactly that, behavior, but I couldn't. Now you can see that I have basically implemented a delay value because I was not able to calculate this because I was setting that value. You can see that I have u set I minus 1 and u I minus 1. So it's not possible to use the values here because they are not ready, and therefore I need to just go ahead and use one sample back, because if I'm entering this saturation, I will be there for quite some time, and after saturation there will be no saturation elements, and you can see that it will settle down to this value, so this will become 0 eventually. Having one sample error does not affect that much of my dynamics here, so I can use this here. Now let's observe the difference, and you can see, even for the integral, you can see that I have a different shape here, and you can see at 2 I have reached already 0, and I have a little movement, and that's it. So basically at this point I'm still trying to adjust my output, but that's not the case here. And I can also see that this whole bump here is not available anymore. We have a saturation, we have a jump, but at that point we are aware of the actual error and integral value of the error. So we are decreasing our control signal because we are approaching the reference. So my error becomes lower. If the error becomes lower, my integral should not be that big, and it just decreases its raw value. So at some point it it enters the linear region of the saturation element, so it applies directly what the control signal on its own was. So that's basically the important part of our implementation. Now I will copy and paste it again, but this time I will show you the other version of my these structures, or these strategies are called anti-wind-up, because it prevents the wind-up, and it does so by adjusting the integrator value or switching the integrator itself off. So it prevents this extra error or extra delay of the system just because of the integrator. Keep in mind that if an integrator has an input that is constant, it will generate a ramp function which looks like a unstable and which is basically unstable signal, because the ramp function has no if you look for the final value theorem, will tend to infinity. Basically, if t increases, if t is tending to infinity, then the output of an integrator with constant input will tend to infinity, and this is not stable. And if, for example, your controller will not be able to, let's say, enter the linear region back of the saturation, or if it's not able to escape the saturation, then your system will become unstable. And this anti-wind-up structure is needed in that case, because the system has linear limitations, which is most of the time the case in real-world applications, and your controller is not aware of this restriction, and your implementation or design method does not involve saturation. So basically what you have to do is you have to just implement an anti-wind-up into your controller. In most of the modern PLCs and in most of the control cards, there are anti-wind-up structures embedded into them. So it's very basic, and it is very important to mention this here. Now the other strategy is to just switch off the integrator. So how can I do that? If I have, let's say, if I is less than this is that. Now, How can I? I'm trying to think of a good version here. If I is less than 3, it says that this is the case, and now if I'm able to go 2 samples back, that means that maybe I will check for equality here. If this is equal to this here, which means that I am in the region, so I will use this integral here because this is already 0. That's why the reason why it works. Else I will just use this part here, so with 0 input basically. So I'm checking for the saturation and the raw data here. If they are the same, then I'm in the linear region, which means that I have no saturation. So I should just use my default integrator. But if that's not the case, if a different value in the saturation and in the raw data exists, then this means basically that I have to switch off my integrator. Switching off means that my input is E here, so giving E 0 just will take care of this part, so this will vanish, and I will have the previous value as a constant here. Hope that this will work. Let's try it out, and you can see it generated basically almost the same here. There is a slight difference because I'm not taking any integral, and these two methods have their differences. Now at this point my control signal does not change that much, but you can see that the integrator has a different shape here. You can see that it has a constant value at that point because it's switched off, and that's going on like that. Now if you switch off this part, what happens basically is that your controller does not have an integrator part, and this means that your control signal is calculated only using the P portion. So that means that you have a P-type controller during saturation. And if you're in the region, if you don't have any saturation, then you're basically back to the PI controller. But during saturation, you will have the P-type controller. Now, these two implementations can be used for that, and we've also basically solved this last task here, which shows us, which says that we should compare the wind-up, the anti-wind-up responses here. You can basically see that there's a big difference, and this is necessary if you have some wind-up. This is the case. Now, I might go ahead and change this to 3, which is basically anti-wind-up structure, and in run 3 we have to change it to 2, and in run 2, as I remember, we have 1. So if I clear CLC and close all, I can maybe run 1, run 2 basically, run 3, and run 4. They should give me 3 different figures, which will correspond to the actual or the non-saturated version of my signals, the saturated version, and basically the wind-up version and the anti-wind-up version here. Now let's adjust them so that we have bigger signals here, and I will be able to compare them at a glance. So basically, I can see now and observe also that the behavior of the system didn't change very much, because my restriction did not allow the overshoot that much, because I had a restriction on the control signal. I can see that a high value for my control signal, or an aggressive controller in this case will hit the saturation a little bit more. A good strategy here would be, since we are talking about real-world applications, a good strategy would be to change your maybe aggressiveness here a little bit. And I can do that by probably changing the rise time here. Let's, for example, increase our rise time so that we have a rise time of 1. And let's say we will have a 3 seconds of setting time. So let me update run 2, run 3, run 4. What is run 4? I guess. So let's say comment. Let's save this, do this. Now let me open up this one here. Hope that I don't mess up anything. So I can see that that did a little bit change. Now I can see that since I didn't calculate the overshoot, but I can see now I'm more around this saturation thing, and I can see that I'm not hitting the saturation that much anymore. You can see here, if I have a saturation, it is almost not hitting the saturation that much, and this is a more ideal control in terms of the saturation, because if you have a restriction, then you should choose your time specifications accordingly. If not, then this will be a bigger problem, this wind-up structure, and it will force you to a certain point. But know about this unwind-up structure, and P-type controller during saturation and API controller during other situations is not a bad idea. So you might want to look for that. And you can also see that your time specifications are very crucial in terms of control and real-world applications, because you are the one who is deciding for setting time, rise time, and overshoot properties. Most probably the system will tell you, or the application will tell you what the overshoot should be. For example, if you have a chemical process, if you're heating a certain substance or chemical compound, then most probably overshoot should be 0, and it should be restricted so that it will never ever overshoot. So the application will tell you if you have a mechanical system and you have a, let's say, robot manipulator, and you should not hit any boundary, then there should be no overshoot. So having no overshoot is most probably a thing that you will take into account. But setting time, rise time, and those things, they are requested so that they will be low in value. So the faster the system, the better it is. But sometimes the application itself has some restrictions on it, namely saturation, slew rates, and etc. So if you think about an industrial application, probably you will try to fasten your system, but that's all. It has a trade-off between these kind of properties, let's say saturation and control signal values, etc. And speed. So this trade-off is up to you. And if you change the settling time, the whole design process will vary, so that you have to choose the optimal solution, and it takes a little bit of practice and some knowledge to accomplish the best, or almost best solution there. So what this lesson basically tells you is that integrators are very necessary, but they have a drawback if you have saturation. And control signals tell much about the system, because if you know the control signal, if you look at the output, the internal signals, you might be evaluating more than you think, because it has too much, it has more information than most of us think. And UT, the control signal, is very important, because if you are in an application, if you are in a control system that needs to, let's say, have a power saving mode, this means that you will look at the control signal and the energy. So don't think of PID controller design of only dominant pole placement, because it's not only about poles and zeros. Most of the time, it is also about the control signal itself and the restrictions of the system. And since the real world is not linear, but only linear at certain equilibrium points and certain uh, operating points, or we are linearizing most of the systems at operating points and equilibrium points. This means that we will have definitely restrictions on some of the signals and internals of the system. So keep that in mind, and it's very important to check out the controller and have info about the system or the process or the application itself. So that's it for this lesson. See you in the next lessons. Have a nice day.